Okay, now let's do example 7.6. It's a very important problem, so you need to pay attention to the discussion. A resistor of 200 ohms and a capacitor of 15 microfarad are connected in series to a 220 volt 50 Hz AC source. And calculate the current in the circuit. Then calculate the voltage across the resistor and the capacitor. Is the algebraic sum of these voltages more than the source voltage? If yes, resolve the paradox. Okay. So what is given? You have an AC source, and then you have a resistor, and then you have a capacitor connected to this. This is R, and then this is C. Okay. What are the things given? The things given are the resistor is 200, this is V. The resistor is 200 ohms, and the capacitor is 15 microfarad. And then the voltage is 220. This is 220 ohms. So whenever we mention voltage is 220, what should you keep in mind? This is the RMS value of the voltage. Okay? So V RMS, that is V RMS, is equal to 220 volts. And this is also is equal to Vm by root 2. So the Vm is different, the maximum voltage is different. And frequency is 50 Hz. So frequency F is 50 Hz. So if you were to write V as Vm sin omega t, how are we going to write it? V is equal to Vm sin omega t, which is equal to Vm sin 2 pi ft. Okay? So what is Vm? Vm is going to be equal to root 2 into 220. So that's going to be root 2 into 220. That's my Vm, multiplied by sine 2 pi, f is 50, 200, so 100 pi t. So my omega is 100 pi. 100 pi radians per second, or 314 radians per second. That's my omega. So this is my V. Okay. So keep this in mind. So this is not what they've given. They've given you VRMS. If they say 220 volts, this is actually VRMS. So this will be 311. Okay. Root 2 into 220 will be 311 sine 100 pi t. So V is actually equal to 311 sine 100 pi t. So that is the equation. Anyway, so that is a side note. What is asked here? So calculate the current in the circuit. Yeah, you can calculate the RMS current, right? So what is RMS current? I is equal to V by Z. Okay. So what is Z now? I have to calculate Z, right? So impedance Z is actually square root of R squared plus XC squared. There is no XL. Okay, so there is no inductor, so it's going to be R squared plus XC squared. XL is 0. Okay. So let's see what are we going to get here. We're going to get R is 220, so 220 squared plus what is XC? XC is equal to 1 by omega C. So that is equal to omega is 100 pi or 2 pi f, you can do it here also. So 1 by 2 into pi into 50, 2 pi f into c is 50 to 10 power minus 6 farads. So this is going to be ohms. Okay, so that gives you, so 212.3 ohms. So 212.3 ohms. That's good. Okay. So if I do this, then Z value is 291.67. So Z value I get is 291.67 ohms. So what is asked? First part is I. So what is I? I is going to be equal to, what is V? VRMS, right? IRMS is equal to VRMS. Is 220 by 291.67. So that must give me somewhere around 0.755 amps. 0.755 amps. So that's the current. Okay. So the first part is done. Now the second part. The second part is calculate the voltage across the resistor and the capacitor. Okay. What's the voltage across the resistor? VR, right? VR, voltage across the resistor VR is equal to I into R. So that is going to give me 0.755 into R is 200. So that is going to give me 151 volts. 151 volts. And what about VC, voltage across the capacitor? That is equal to I into XC. So again 0.755 into XC is 212.3. 212.3, and that gives me 160.3 volts. So this is RMS. This is RMS. Okay, or RMS volts. So 220 is the input RMS voltage, but you see VR is 151 volts. And VC is 160 volts. On 60.9. 220 you are applying, 151 plus 160. It is more than 220. Is Kirchhoff's law not obeyed? This is not equal to the sum of these two. The algebraic sum is 151 plus 160 with 311.3. The applied voltage is 220 volts. How can this even happen? Kirchhoff's law says that in a closed loop, the voltage must be equal to 0. So if this voltage must be equal to the voltage here applied across these two terminals. But that is not the case if we algebraically add them. So what is happening here? I want you to draw attention to the phasor diagram. Suppose this is my eye. How will the phasor diagram look like? This is my eye. This is my eye. And my voltage VR will be in phase with the current I. So this is my VR. Correct? But what about my VC? My VC, this should be voltage across the capacitor. That must be lagging the current. So my VC is here. This is my VC. So there is 90 degrees between VR and VC. And what is this? This must be the vector sum of the phasor sum, I should say, of these two, right? So clearly, we do is this must be my V. So you have to remember that this voltage is not in phase with this. So when there is Vm here, this is not Vm. Okay, when you have Vm here, this is 0 actually. This VR is 0, you see, the projection is 0. When Vm is here, this projection is 0 here. So you have to remember that. So they are not in phase. Okay, so that is why the phase diagram comes very handy. So VR, I've chosen I, VR must be the same phase as I. But VC must be 90 degrees to I. But VR plus VC must give you your applied voltage V. So that is here. So there would be a phase difference phi. It's different. Okay? So the applied voltage will lag the current. Or we are going to say this is sin omega t, then this will be sin omega t plus phi. Because this is leading the voltage. The current is leading the voltage. So that is how it is. Anyway. So what is V now? So V is actually square root of VR square plus VC square. So that will be equal to 151 square plus 160.3 square root. So that is going to give you 220. Okay. So you cannot simply add 151 and 160 straight away. In an AC circuit, this cannot happen. The VRMS volts cannot be added algebraically. They have to be added like this, using the phasor diagram. So you have to know that VR and VC are not in phase, and there is a phase of 90 degrees. VC lags VR by 90 degrees. So the resultant is actually VR, you see, it's a vector sum. In this case, a phasor sum. Then this would match. So Kirchhoff's law is obeyed that way. Okay? So notice here, I want you to understand this. So you are not taking the instantaneous values of voltage. At every instant, if you just take the time I am seeing the voltage. If this is 10, then this must be 8 and this must be 2 or something. Okay? At every instant, Kirchhoff's law will be obeyed. But here, you are not talking about the instantaneous voltages. We have taken the RMS voltages. So the RMS voltages are not instantaneous. So how to make the RMS voltage match is like this. So you have VC, you have VR, then you add them, you have a phasor addition of these voltages. Then this RMS and this RMS will be equal to this RMS. I hope this is clear to you. This is a very important problem. When voltages are mentioned in RMS values, you cannot just algebraically add them. You have to draw this phasor diagram and add them in a phasor manner. Okay, you have to add them like vectors. Then this will be equal. So this is how it has to be done. So keep this in mind. Don't forget. Okay. In an LCR circuit, we have been talking about natural frequency and resonant frequency, and we also say that omega naught is equal to root of 1 by LC and all that. So if there is a resonance, then there must be something which is oscillating. So the system must be oscillating, and there is an external source that is providing energy to that system, and if this frequency and that frequency are the same, then resonance will take place. And we also calculated the natural frequency omega is equal to 1 by root LC. But we have not talked about how an inductor and a capacitor together perform these oscillations. We said the circuit must have an inductor and a capacitor in series. Only then can you have oscillations. That's what we said. But we have not explained how this happens. That is what we are going to do now. See, LC oscillations is what we will look at now. So what I'm going to do now is that I'm going to take a capacitor and I'm going to connect a battery to the capacitor. So the battery will start charging the capacitor, and once the potential across the capacitor equals the potential of the battery, then the charging will stop. Then you will have maximum charge on the capacitor. So that is what I do. So I have taken a capacitor and I am going to connect a battery to this capacitor. So this is capacitor C and this is battery V, and this is going to charge this capacitor. So I'll have I can charge Qm on the capacitor. The steady state, this capacitor will be fully charged, so we'll have maximum charge on it now. So what I'm going to do now is I'm going to remove this battery. So if I remove this battery, the voltage will still remain because this capacitor is charged. So CV is equal to Q. So the voltage is equal to Qm by C, which is the same as the voltage of the battery you used to charge this capacitor. But you have removed the battery now. Now I am going to connect an inductor with this. So what will happen now? An inductor is basically a conductor. So you have provided a path for the capacitor to discharge the charge accumulated. Right? So there is going to be a discharge here. So current I will start flowing in this. But before it starts discharging, this will have certain energy. So what is that energy? I call this as the potential energy stored in the capacitor. I'll call this as UE. Okay, because electrical energy, right? This is. So this UE is given by Qm squared by 2C. So in the beginning, this is what you will have. And what's energy in the inductor? Energy in the inductor will be in the form of the magnetic field, but you have not started sending any current yet. Okay, it does not start yet. Let me just keep it open right now. This is kept open now. So there is no energy in this. So in the beginning, the energy in the inductor will be equal to 0. Okay. So now you are closing it. Closing the circuit. So when you close the circuit, then it becomes a closed loop and the capacitor will start discharging this charge. So what will happen? Let me take the first case. The first case is, in the first case, I'm going to draw a graph. Okay. In the first case, you have, this is energy level, okay. So you have all the energy is electrical. This is the, so all the energy is electrical. So this is your UB, but that is 0. There is no energy in this. Now it starts discharging. So the current will start building up from 0 to some other value. Okay. It will start increasing. As the current starts increasing, then I will have a different configuration now. So what will happen now is, this is a capacitor and the current has started flowing. So this is the inductor. As the current starts flowing, then I'm going to have a magnetic field around it. Okay. So there is a magnetic field in that. So current is flowing in this direction. So this current is flowing in this direction. So the field will be like this. Okay. You have and as the current starts flowing, this current, initially the current is 0, then the current starts flowing. As the current starts flowing, you have some current I here. Suppose I have lost half the charge. Let's say I got only this, plus, minus. Half of this time. So what will happen is that this charge will, as the current starts flowing, this energy, now you have reduced charge now. Since you have reduced charge, this energy would be Q, whatever Q you have now. So you don't have Q maximum, now you have some Q squared divided by 2C. But you have built up a current I. So then what is the energy in the magnetic field? We have done that already, right? UB is equal to half L I squared, whatever current is. So now in the second case, this is case 1, and in the second case, what happens is that you have this kind of graph. The second case, you have, this is maximum, you don't have a maximum, so this is U max, okay, which is equal to this U value anyway. So now you have something else now. This has come down, your UE has come down. Now you also have magnetic field. After energy is there. So there is, initially all the energy was the capacitor, now half the energy is the capacitor in the form of charges, and half the energy is now in the form of current in the magnetic field. Okay. It is, so you get that too, and you continue to lose charge now, because you provided the path, this charge will continue to go to this side. So what happened now is that third, you are going to lose all the charges. You are going to lose all the charges now. Okay, so now I has reached its maximum value. There is no charge here, but then you are building up current. So I will have the maximum value here. So you will have, this is going to be stronger, much stronger than before, this magnetic field. So in this case, when all the charges, all the positive charges have gone there and then balanced negative charges, when there is no charge here, then the energy in this is equal to 0 because there is no charge in this capacitor. But then what has happened here? All the charge now has become current. Okay, see, in the sense like it's going to be, all the energy that you had here is now stored in the magnetic field. So half L, now you get Im squared. So this energy must be equal to this energy because you lost all the energy. This energy has been used to build up this magnetic field. So the energy is now the magnetic field. Okay, so 3 is this. This is Em. Okay, this is Ue, and this is U. Okay, third is going to be okay. So third, the Ue is 0. There is nothing in it. The Ue is 0. And here, your UB will be this. Everything will be in magnetic field. Okay? So there is no charge on the capacitor. All the charges have come and balanced here. Then what are you going to do for the next one? There is no charge, but then the current is flowing in this direction. So the current will not become 0 because you see you have an inductor here. The inductor will not allow the current, will not allow, rather it will be against the current changing direction. Okay, or current reducing. The change in current will be opposed by this inductor. So what will happen is, even though there is no charge, now the magnetic field will shrink, and the energy in this magnetic field will be used to put the current in the same direction. Okay. So what happens now is that this will start putting the current here. Like, there is no energy here. All the energy is here. Current is flowing in this direction. Now the magnetic field will try to maintain the current in the same direction. Okay, because it is against the change. The magnetic flux will be, that's Faraday's law, right? So it will be against it. So it will continue to put the current in the same direction. But then the magnetic field will stop shrinking. Okay. So then what happens now is, next you have this curve. Okay. You have inductor here, and the current would be maintained in the same direction, but then the magnetic field will shrink. To maintain the current in the same direction, you need to spend energy. So that will, magnetic field will shrink now. Okay, will shrink. But then the current will be maintained in the same direction. Okay. So as the current comes here, now you see the positive charges will be put here. Here. And I've got negative charge here. You put positive charge here, and then will be negative. So now if you notice that UE will have, let's say I have some charge Q here. And UE will now be equal to Q squared by 2C. And then UB is equal to half Li squared. Now I lost some energy. That energy has gone to the capacitor. Now the capacitor has some energy. I lost energy in the inductor. So now we have reduced current. I had maximum current when this was 0, but now it's continue to maintain this by losing the magnetic field. So this I will also come down, but then that will put charge here. So part of the energy would go here and the remaining energy would be here. Okay, so in the halfway condition, I can take that this is this UE, and this is the maximum, and this is half the energy. Now in this condition, I have half the energy in the electric field and half the energy in the magnetic field. So sum of these two will be equal to this or that. Okay. So law of conservation of energy should hold good. And now it will continue to do this as the magnetic field continues to charge this capacitor, it will lose itself. The energy will be lost in the inductor. So now what will happen is, there is a capacitor here and an inductor here. See, now you lose all the magnetic field, then you will charge the capacitor like this. Okay, the capacitor will be charged to maximum QE. Now UE will be equal to Qm squared by 2C, and UB will be equal to 0. So all the energy that was there has now gone to the capacitor. Okay, here this would be 5. So now I have everything in UE, and UB will be 0. Okay, note that I am reversing polarity. I started with this positive and negative, and then I come down, come to this position where I have positive charges on this plate, negative charges on that plate, and there is no current here. But now, what will happen? The same thing will happen in the opposite direction. There is no potential here, so you are charged it to the maximum, then this will start pushing the current this way. Okay, so then it will lose this energy, and then the current will start going in the opposite direction. The magnetic field will be built up now, and it will become 0, and it won't allow the current to reduce, so it will continue to put the current in the same way. So you will continue to charge this capacitor, okay, and there will be an halfway, and finally when you lose all the magnetic field, then this will become positive and this will become negative, then you will come back to the original position. Then this will continue. So this is half cycle, and once this is there, then the whole thing would be done in the opposite direction, and this will be charged positive. And once it is there in this direction, then it will start doing this, and it will come here. Then the current direction will change. Then you will go there. Then you come here. Then you go there. Then you come here. So you see, oscillations will take place. So a simple LC circuit will result in oscillation. You charge the capacitor, connect the inductor to it, then oscillations will take place. If there is no energy loss in it, like there is no I squared R loss or radiation loss in this, then this will go on forever. This oscillation will continue forever, for infinite time. But nothing is ideal. So as the current flows back and forth, you are going to have an I squared R loss. The energy is going to be dissipated in the circuit. So you will start losing energy as heat, and finally no energy will be there in the circuit. But that is the reality. So, but what I want to tell you is, when there is no resistance in this circuit, and there is no energy loss, then energy in the capacitor will shuttle between the capacitor and the inductor. It will go to the inductor from the capacitor and from the inductor to the capacitor, and capacitor to the inductor, from the inductor to the capacitor. So it will be shuttling between these two things, and you will be having graphs like this. Okay, so this is what the LC oscillations are about. Now this is where the oscillations come in. This is where the system tends to oscillate, and then you bring an external source. So this will oscillate with its natural frequency, and you are going to bring another source like an AC source or something. Then resonance can take place. Okay? I hope you understand why an LC circuit oscillates. Okay, you had a qualitative understanding of the LC oscillations, and we will do it quantitatively now. So I have this capacitor. I'll take a different pen. I have this capacitor, and then I also have an inductor. See? And suppose this is charged positively. So the voltage is positive here, negative here. So as per Kirchhoff's law, this has to balance, so this will be positive and this will be negative. So I'll call this as VC, and then I'll call this as Vn. So if I apply Kirchhoff's law, I'll start from here and I'll come back to the same position. So I'll do it clockwise. So Vn, okay, I come here and then I enter negative. So the negative terminal, right? So Vn minus Vc must be equal to 0. This we know from Kirchhoff's law. But what is Vn? Vn is minus L di by dt. And what is Vc? It is simply Q by C, and that is equal to 0. If I take the negative sign there, then I will get L di by dt plus Q by C equals 0. So this is the expression I get. So this is the expression for this mathematical equation for this circuit. Okay? So I got di by dt. Well, how can I write di by dt? Well, I is dq by dt. So di by dt must be equal to d squared q by dt squared. So I put it here. So L d squared q by dt squared plus q by c equals 0. Okay. So I'll do some more manipulation to this. So that will give me d squared q by dt squared, if I divide all of it by L, plus q by Lc is equal to 0. And if I take it to the other side, then I get d squared q by dt squared is equal to minus q by Lc. Okay? Or I can say this is equal to minus 1 by Lc into q. Note this, d squared q by dt squared is equal to minus 1 by Lc to q. Okay, this should remind you of the simple harmonic motion. So remember, in the simple harmonic motion, acceleration is proportional to negative of the displacement. We got this in simple harmonic motion. Okay. Acceleration was proportional to negative of displacement. Okay. So then it's with this actually d squared x by dt squared is equal to minus then kx. So this is the expression for simple harmonic motion. So this is also, this resembles simple harmonic motion, but in this case you got charge, there you got displacement. But this is the expression. But when you have an expression like this, then what does this give you? This is actually, this is equal to d squared x by dt squared is equal to minus omega squared k, omega squared x. Okay, so this is actually omega squared, the angular frequency of the simple harmonic motion. Okay, so omega squared here is equal to 1 by LC. So omega is equal to 1 by root LC. So this is what we called as the natural frequency of this oscillation. So we will explain that mathematically here. Okay. So from this, then you can find the nature of Q, right? Okay. What would be the equation for Q? The solution for Q? From simple harmonic motion, I can say that Q is equal to Q max into cos omega t. Remember? Because when time is equal to 0, you had Q maximum, and then as time increased, then it started decreasing. Okay, so when time is equal to 0, Q was equal to Q max, and it was reducing. So Q is equal to Qm cos omega t makes sense now. Okay, so I can find current. Current would be dq by dt is equal to minus cos omega t minus sin omega t to dqm by dt. So there will be maximum current, and you can do all that with this. So this is a solution for that. The point I'm trying to drive is this LC circuit exhibits simple harmonic motion. The oscillation is simple harmonic with an angular frequency omega equal to 1 by root LC. So this is the quantitative treatment of this circuit, and we also saw qualitatively what was happening. Okay, so mathematics tells you that there must be an oscillation, because you see, when you manipulate this equation, you get this expression, and this is the expression for simple harmonic motion. So this itself tells you that there must be oscillation going on between these two. Okay, and we saw physically how it was happening just before that. Hope this is clear to you. Let's do example problem 7a11. Show that in the free oscillations of an LC circuit, the sum of the energy stored in the capacitor and the inductor is constant in time. Okay, let's see. So I have, this is 711. I have the capacitor and then the inductor circuit. This is C and this is L. And to start with, I have Q maximum, and that will get converted into current, and the energy will be shared between these two things, and all that will happen. So Qm is the charge you start with. Okay, so if you close it, then current will start flowing. So this is the condition. So from the solution to this equation, d squared q by dt squared is equal to minus 1 by LC into q. In this equation, we saw that q at any time t is given by q max and then cos omega t. Okay? We did that. And now, if q is this, and then what is current at any time? I of t is equal to dq by dt, and that is equal to qm is a constant maximum charge. That doesn't matter. That's maximum charge, right? So you started with that value, qm. It's amplitude kind of thing for this function. Cos omega t will be minus sine omega t into omega. So your I of t is equal to minus qm omega into sine omega t. Okay? So now, what's the energy in the capacitor? Energy in the capacitor at any time is given by UE is equal to Q divided by, or Q squared divided by 2C. And what's energy in the inductor? That is UB, that is given by half L I at any time squared. Okay? So UE can be written as, instead of Q of t, I'm going to put this. So that's going to be Qm squared cos squared omega t by 2c. Okay? And what about UB? UB is equal to half L. Instead of I am going to put this stuff minus Qm omega sine omega t the whole square. So what is it going to give me? It's going to give me, this is going to be Qm squared and this is going to be omega squared and this will be sine squared omega t. Okay? So this is what I get for I. Okay. So what is omega? Omega, if you remember, omega is equal to 1 by root LC. So omega squared will be 1 by LCM squaring it. So I'm going to put this here. So half into L into Qm squared into omega squared is going to be 1 by LC into sine squared omega t. Okay? So this cell and this cell cancels, so that this is equal to half Qm squared sine squared omega t. So what is this? This is energy in the capacitor at any time t, and this is energy in the inductor at any time t. So that's UB. So what's the total energy? So the total energy will be the sum of these two. At any point in time, the total energy is the sum of this energy plus that energy. When I add these two, let's see what I'm going to get. The total energy U is equal to UE at any point in time, and then UB at any point in time, and that is going to be given by Qm squared cos squared omega t by 2c plus Qm squared sine squared omega t by 2c. By 2c. When I add these two, then what I'm going to get now? I'm going to get Q em squared by 2c into cos squared omega t plus sine squared omega t. So this is actually 1. So that will give me Qm squared by 2c. That's my total energy. So this is a total energy at any time. You see, it doesn't have t in the expression. It's a constant one. So this doesn't change with time. So this changes with time. ue will change with time. ub will change with time. But the sum of ue and ub will always be qm squared by 2c at any point in time. And that makes sense. What is this energy? And this is energy you charge the capacitor with. In the beginning, once it is charged, then you had this energy, right? So this was, the energy on the capacitor was half qm squared by c. And this is what you had. You started with this. And only this energy had to be shared between the capacitor and inductor. The whole thing will become this. And that will become this. So at every and any point in time, this should hold good. So this is what you have to understand from this problem. Okay? Okay. And on top of it, I want you to take a look at table 7.1, where they compare the mechanical systems with electrical systems. And then they tell you that there is an analogy that you can come up with. Okay, if you look at the expressions for the mechanical systems and the electrical systems, there are certain analogies that you can realize. Okay, so I want you to go through that. I want you to go through table 7.1 and also the topic on two different phenomena, same mathematical treatment. Because the mechanical system and the electrical system will have the same mathematical equation, same type of mathematical equations. Quantities will be different, but then they will have the same type of equations, the differential equations. Okay? So I want you to take a look at that too. Hope this is clear to you.